All right, so we fast forward to basically the time of the Renaissance, um, to what's called the heliocentric model. Copernicus is the first one who, in recent times, used this idea that the sun was the center of the solar system. Um, well, the center of the universe, really, because they had no idea what the stars were, but that's heliocentric. It just means the sun-centered solar system, and so it turns out that if that model is correct, it's only the moon that is going around the Earth, um, and the Earth is just a planet, just like all the others, and goes around the sun. The sun is the center, and that's why it's heat. Yeah. All right. Anyhow, you get it. So one of the first things that Copernicus does is he's able to explain retrograde motion for the very first time, in a way that doesn't involve little circles inside of circles. The epicycles. So the way he explains it is really, the way I always talk about this is, imagine you're going around a giant curve, like you're driving along and you're about to go onto the interstate, and so you're going around this ramp, and it's a big huge curve, and let's say there's two lanes. You're going along. If you are the car that's on the inner lane, and you pass a car that's going on the outer lane, and assuming you're like in the driver's seat because you want to be paying attention to the road, but you're in the driver's seat. You're in the passenger seat in the car, in the car that's closer to the radius of the circle, right? So it would be like the inner car, and as you're going around, if you looked at the car, I mean the car on the outer lane is still moving forward, but if you were to compare the car to the guardrails, which are fixed, as you pass the car, for a very brief instant, it would seem as though the car were moving backwards with respect to those guardrails. And that's the explanation for retrograde motion. So the planet never turns around and goes backwards. What we're seeing is the planet seems to be going. It's basically an optical illusion. It seems to be going backwards, but that is really more about the motion of the Earth compared to the planet. And so when the Earth overtakes a planet, it'll seem to in its orbit, it'll seem to move backwards for a certain amount of time. All right, and that's the explanation of retrograde motion, and that worked very, very well. Okay, now not everybody accepted this at first. When Copernicus first proposed it, he was so fearful that he actually waited, or he was literally on his deathbed before they brought him the book, and about this Copernican revolution. All right, so let's go over some of the highlights of his book. First of all, it says the Earth is not the center of the entire universe, which we definitely know that's true now. So the Earth is the center of the moon's orbit, and all planets revolve around the sun, and of course the Earth being one of them. The stars are much further away, and they didn't have any idea how far away they were. The apparent motion of the stars around the Earth is really due to the Earth's rotation, so we're rotating about its axis once every 24 hours. The apparent movement of the sun around the Earth is of course due to the Earth's rotation. The same 24-hour. That's the motion that we observe, right? From the sun rises in the east, it seems to set in the west, but that's really us rotating from the, rotating counterclockwise, if you will. Like if we were looking down at the solar system, we're rotating about our axis counterclockwise, and we're also going around the sun in the same direction as well. All right, so again, retrograde motion is just due to the Earth's motion around the sun. It's just the way that we, this picture is kind of showing it, that it would appear as though the planet starts to move backwards as the Earth, overtakes the planet in its motion. All right, so that's Copernicus set this up. For a long time, Copernicus wrote this book. As I said, he was very fearful, and he actually that sense of fear was actually turns out probably pretty unfounded at first. It really took about 100 years or so, and when we get to the time of Galileo, that this becomes a really big issue. The main idea around the world was not one that Copernicus was the geocentric model was the one that had dominated for over 1,000 years, close to 2,000 years, and so this wasn't going to go away with Copernicus's idea. All right, so here, hold on. Okay, so again, we were talking about the Copernican revolution. So really, retrograde motion is really just optical illusion. The planet never, stops and moves westward. It just appears to do that, and that's really because of the Earth's motion around the sun. All right, so it's the year 1609. Galileo, who this is a good 100 years or so after Copernicus, doesn't actually invent it. He doesn't invent the telescope, but he hears about it, and he builds one of his own, and he goes out and begins to look at the night sky in 1609. And he observes many, many different things. A very significant thing here is, it might not seem like it's that significant, but he notices that there are mountains and valleys, and in fact he sees craters as well on the moon. And one of the significant things, I think, that it turns out that in Galileo's, he writes a very popular book. What he does is he talks about when he made these observations, he compared the moon to looking at the mountains and the valleys of the moon to the Earth, to the Italian countryside, and the reason that that's significant is for all times before Galileo makes that comment. The objects in the heavens were completely different from the Earth. So this actually leads people afterwards, like Isaac Newton in particular, to realize that the laws of physics that we learn about on Earth are applicable to the heavens as well. All right, so that's a very significant thing as far as I'm concerned. About this what's going on on other worlds applies to the physics of it. Anyhow, it applies everywhere. He also observed sunspots, which turned, and he noticed that the sun was rotating. That's another important observation. It's actually unfortunate that he used his telescope to look at the sun. He probably looked at the sun when it was towards the horizon. It's actually a really bad idea to do that. he had actually ended up going blind the last 10 years of his life, and a lot of people think it has had to do with the looking at the sun through his telescope. Another very significant observation that he made is the moons of Jupiter, and there's some drawings over here where Jupiter is the large circle, and these little star-looking objects. He noticed that they all lined up in a particular plane, and he would look the next night, and some of them have moved, and then others, sometimes you couldn't see them because the moon was actually behind Jupiter, and so he observed these over many nights, and kept observing them actually over a long period of time. And so these became known as these four large moons. These are the four largest moons of Jupiter. They became known as the Galilean moons. All right, they are Io, Europa, Ganymede, and Callisto. We'll talk much more about those when we get to the chapter on Jupiter. The other thing that he noticed was the phases of Venus. So Venus doesn't appear as a complete disk. Here's a nice picture on the PowerPoint. So the thing is, if you go back and you think that the geocentric model is correct, right? Everything goes around the Earth. Then why would Venus have phases? It doesn't make any sense, right? So there's no way to explain it with the geocentric model. Only the heliocentric model, the idea that the Earth and all the planets go around the sun, that the sun that's the only way that you could explain phases of the moon. I'm sorry, of Venus, not of the moon. All right, so that is so that that's. This is showing what it. Yeah, this is showing. All right. All right. Let's see. So let's get to Kepler. We'll do the next couple of minutes about Kepler. So Kepler's laws. Kepler actually used observations made by a contemporary of his named Tycho Brahe. Tycho Brahe is the last of the just naked eye observational observers. So he didn't actually have a telescope. So he made all of his observations in this castle, and this is actually a picture of his. It's kind of like a giant sextant. If you've ever, it basically tells angles of different objects in the sky. Anyhow, so Kepler, Tycho Brahe had done years and years of observations. In some cases, like Mars, for example, he had accumulated over 20 years of data. And Kepler, when Tycho Brahe dies, Kepler, who actually had met Tycho Brahe, basically got that data and was really pretty much one of the only people on the planet that could use that data, so he made some observations. And remember, the ancients thought that everything moves in perfect circles, and no matter how Kepler tried to match the data, and this is, a lot of people think of Kepler as one of the very first true scientists of the modern age, because he thought that just like the ancients, that the planets moved in perfect circles, right? But he couldn't get the data to fit that, and he knew the data was as accurate as you could get from Tycho Brahe's observations, and so he realized that the data showed that the planets don't travel in a perfect circle, but in kind of an elongated circle called an ellipse. And so that is actually his first law of planetary motion. Planets travel in elliptical orbits as they go around the sun. And in fact, it turns out that one of the focal points, so this is how you can draw an ellipse, one of the focal points is what's called that would be where you find the sun. And so there's another distance called the semi-major axis. So that's kind of halfway between the two foci. Okay, so that distance right there, that's going to become important to us for the second law, which I'll get to in the next video.